Without further ado, I'd like to welcome Arun Gupta. Arun is the founder and CEO of Skyven Technologies. And as all things in energy of this, I keep calling it a podcast, this LinkedIn Live event, is we want to bring you the information and education that you need to better address your energy needs, your energy efficiency, and of course, most importantly, your decarbonization goals. So starting off, Arun, tell us a bit about Skyven Technology, and then we're going to jump right into your new developments.
Awesome. Yeah. Well, thanks, Dave, and thanks for having me here, and I appreciate that the time and attention from everyone on the meeting here. So I'm my name, thanks, Dave. My name is Arun Gupta. I'm the founder and CEO here at Skyven Technologies. We are an energy as a service company that delivers clean, emissions-free process heat to industrial manufacturers, and we do that at prices lower than natural gas. So in order to do that, we install the latest clean thermal energy technologies on site at the manufacturing facility. And we bill for the thermal energy those systems produce. And again, we bill at lower than the prices of natural gas. So our customers save money from day one with no capital expense, and they make progress on their carbon goals without spending any money.
Fantastic. Arun, help me to understand sort of just the scope of the market. Industrial process heat, and I'll put it, and of course I'm putting you on the spot here, but as a percentage of, let's say, global greenhouse gas emissions, what percentage is industrial process heat?
Roughly 20%.
Wow.
It's huge. It's about as much as all of transportation, almost as much as all of transportation. By all of transportation, I mean all the cars, trains, planes, boats, everything combined. It's huge.
Why is industrial process heat such a difficult nut to crack related to sort of like decarbonization?
Yeah. I mean, industrial heat is, it's considered one of those hard to decarbonize sectors.
But it's a quarter of the total greenhouse gas emissions. We got to do something, right?
We got to do something. Yeah, we absolutely. There's basically no option otherwise. The reason why it's been so hard, there's a couple of reasons. One is that in the industrial sector, manufacturing operations have such high uptime requirements. Downtime in an industrial manufacturing facility is incredibly expensive, and industrial manufacturing in general tends to operate at thin margins. And so doing anything different at an industrial manufacturing facility or changing the facility has a high risk and high possible expense. And that's been a barrier against taking action. And I guess in general, like speaking even at a little bit of a higher level there, we either haven't had the technology to decarbonize industrial heat, or where we do have the technology, it hasn't made financial sense. Mm-hmm. And that whole, uptime, downtime thing really plays into, does it make financial sense?
So as the IRA was out, we look at all the incentives, and I'm going to say it this way: heat pumps are all the rage. Everywhere I go, we're talking heat pump. Now, your energy as a service for industrial process heat, we help on the electricity side. And we're seeing a lot of building owners and things, especially in places like New York and Boston and Chicago, where they are in fact now passing legislation for decarbonization, energy intensity, with penalties if if your building goes over it and things like that. So we're seeing a lot of interest in heat pumps. I'm going to call it in the residential, commercial kind of thing, but it's quiet. And I don't mean that in a negative way, just quiet on the industrial side. So why haven't we seen the same level of interest in heat pumps on the industrial process heat side, at least today?
Yeah, I mean, that's a great question. I think like to date, it's been a function of the temperatures that industrial heat pumps have been able to achieve. So most industrial facilities are using steam to transfer heat around the plant and get heat to the process that needs the heat. And steam is pretty hot. Steam's running 300 degrees, 400 degrees Fahrenheit. Whereas the heat pumps, most of the heat pump technology out there is suited for space heating, right? Because, it's really targeted towards commercial and residential heating, which is, keeping us comfortable. What temperature do you and I need? Like, we need 70 degrees Fahrenheit, not 300.
I think if you were in Texas right now, they would probably hoist you on their shoulders and parade you around if it was 70. But
yeah. I mean, it's Texas is brutal right now, but yeah. So the challenge there has been that heat pumps just haven't reached the temperatures that industrial manufacturers need, and that's been a barrier to heat pump adoption.
Well, a heat pump is literally moving heat. So it's moving heat from one reservoir to another. And in doing so is increasing the temperature. And if my memory serves me correct, the differential between that sort of the source reservoir and the sink reservoir is called the lift. So when you're saying, like, if I was a residential, I want 70 degrees, outdoors is maybe 30 or 40 degrees, I've got a lift of, 30 or 40 degrees, right? So classically, what is sort of the limitation on heat pump technology on that lift? And then how do we get it to that 300-400 degrees that you're talking about?
Yeah, I mean that's exactly the challenge, right? The lift, for a space heating heat pump, right? You've got 30, 40 degrees lift. For an industrial heat pump, we need something like 200, 300 degrees lift. So that's just another ballpark. And through there are a number of different heat pump technologies out there, but the one that is mature, uses the vapor compression cycle. So it's using compressors to pump up the temperature of the heat. And so, what we need, in order to achieve the higher temperatures is either more compressors or compressors with higher compression. And that's what we do here at Skyven. So Skyven has a heat pump technology that we're pioneering. It's called Skyven Arcturus, and it is a large-scale industrial heat pump that's able to generate temperatures as high as 400 degrees Fahrenheit in order to generate steam that we inject directly into the plant's steam header. And in order to get the high lift, in order to get up to temperature, because we start at temperatures 80 degrees Fahrenheit is a common temperature that plants have a lot of heat at 80 degrees. They can't do anything with it. And so we take that heat and pump it up. So that produces a lift of 200 to 300 degrees Fahrenheit. In order to get that lift, our Arcturus heat pump system puts a large number of compressors in series in order to pump the temperature up and up and up and up until we get to 400 degrees.
So one of the classic sort of metrics on heat pumps is its COP, its coefficient of performance, right? So how does yours compare to regular heat pumps? How does it compare to my alternative, which I guess is just a steam boiler?
Yeah, so let's talk about the steam boiler first. So the steam boiler is converting natural gas into steam. And a typical steam boiler has an efficiency of around 80% in an industrial steam boiler, which means it has a coefficient of performance, a COP of 0.8. On the other end of the spectrum, you've got a traditional commercial heat pump, which typically has a coefficient of performance, a COP 3 or 4. Is pretty typical. The heat pumps that we do, these high lift heat pumps, their efficiency is limited by physics. It's a term that we call like the Carnot efficiency is the technical term,
Right.
but it's the maximum efficiency you can possibly get if you had a perfect system. And for the types of, depending on the lift, the types of systems we do, Carnot limits the COP to, somewhere around 3. That would be the perfect COP if you built a theoretically perfect system. Skyven's Arcturus steam generating heat pump achieves about 75% of Carnot, meaning like we're able to get 75% of the way to the perfect system. Where, for context and comparison, most of the other high lift industrial heat pumps that are in research and development today are in more the 50 to 60% range. So we're able to achieve much closer to the theoretical maximum based on the approach that we're using.
So let me run some numbers quick in my head then. So if the ultimate Carnot efficiency, theoretical Carnot efficiency, COP is 3, you're at 75%, I'll call that 2.4, compared to, you said the boiler at 0.8.
That's
so
right.
We're talking almost a 3x increase in overall efficiency. Is those numbers kind of jive?
Those numbers are right. Yep, you nailed it.
Right.
Yep.
So you're talking to an industrial process heat people, and you're saying, I literally can increase. Now, we're just talking this from a thermodynamic efficiency perspective. Improve your thermodynamic efficiency of your steam system by a factor of 3. Is that somewhat accurate?
That is accurate. So that we are increasing the thermodynamic efficiency by a factor of 3, and that's what basically enables these heat pumps to make economic sense, right? Because at the end of the day, a industrial manufacturer, what they really care about is the reliability of production of steam and delivery of steam to their manufacturing facility, and then they care about the cost.
Yeah, I'm going to get the cost. Go ahead.
Yeah. So I might have jumped the gun on you on cost.
Yeah, no, that's all right. That's all right. No, I'm setting you up. I'm just setting you up.
Yeah. Well, I mean, so the cost is a challenge there because this system is 3x more efficient than natural gas. Electricity can cost 3 times more per the same, essentially the same unit of energy as natural gas, and we still end up with cost neutrality. And so that's what we call the term you may have heard is spark spread.
Right.
The difference in cost between natural gas and electricity. You also hear it referred to as the heat rate in the power sector. And in our case, we can tolerate a spark spread that is about the same as a COP. So if we have a COP of 2.4, versus 0.8, like you mentioned, we're 3x more efficient. We have cost neutrality where electricity costs 3 times more than natural gas.
So to put you on the spot in that regard, are there certain areas of the country where I'll call it the spark spread or the infrastructure and natural gas electricity prices are most conducive to me replacing with a Skyven system?
So what's really interesting, and I know that this is a lot of what Exergy does as well, is that in certain places in the country, there's what they call index electricity pricing, where the wholesale price of electricity changes every 15 minutes. And as we put more and more renewables on the grid, renewables don't have a fuel cost, and so they have the ability to produce energy at very, very low cost. And so they actually during the summer on a sunny day, during noon on a sunny day, you oftentimes end up with low-priced electricity because you've got a lot of solar that's producing electricity. And so the advantage here of the heat pump is the heat pump can take advantage of that low-priced renewable electricity. And so that's one great use case, is that sometimes, like in California anyway, there are some days where the price of electricity actually drops to zero because there's so much renewable energy on the grid, and that's a really cost-effective energy source, is zero price renewable energy. And then the other good application is where there's a lot of hydro available, because hydro, as long as you're not in a drought, hydro is a really cost-effective energy source, and so that systems tend to work well there as well.
So, sort of putting you back on the spot, since you brought it up with solar, right? And you're in California, we'll bring up the duck curve. So yeah, we've actually seen electricity rates during the day and high sunny days actually go negative. You're from Texas originally as well. And Texas, we've seen negative electricity rates at night when there's a lot of wind. So we've never seen natural gas prices go negative. Okay, so let's be honest there. So the economic efficiency performance can be substantially better than during these periods of let's call it abundance, right? When I've got extremely low cost energy. So not only am I 3x on efficiency, I am almost negative on my energy cost in general. Let's put it that way. However, the nasty part of the duck curve is when the solar rolls off and the wind hasn't picked up yet. This huge ramp time, which we're seeing, for example, in ERCOT right now, between 5 and 9 p.m., prices have been now at $5,000 a megawatt hour and things. So the old thing is there's no free lunch. So what giveth doesn't it taketh away, meaning, hey, cheap solar in the day, cheap wind at night, but I'm going to get killed during this period of the ramp. What's the play there?
Yeah, great question. That ramp, the neck of the duck, as they call it.
Yeah.
So the opportunity with a steam generating heat pump is that it is fully redundant with and backed up by natural gas boilers.
Okay.
That's done for reliability purposes, but it can be leveraged to address exactly the challenge that you're discussing, Dave. So, at say 4:35 p.m., where you got electric load spiking, climbing up the neck of the duck, we can actually turn the system off.
Okay.
And revert back to the natural gas boilers, because natural gas prices, do not change every 15 minutes.
That's right.
So you've got a flat natural gas price, and during those hours, 5 p.m. to 9 p.m., typically natural gas is the cheaper energy source, even with the COP factored in. And so it makes sense to utilize that lower cost energy source when it's lower cost. And then at night hits and you've got the wind ramping up, let's go back to the renewable energy source. And it's a great way to transition between fossil fuel, natural gas, and renewable electricity.
Would your system or customer or Skyven then be able to participate in things like demand response, or also, whether it's economic demand response or emergency demand response and things like that, and get additional revenue generation from the grid?
Yeah, absolutely. Because these systems are backed up by natural gas boilers, and the natural gas boilers are kept ready to go, we're actually able to switch over to natural gas boilers pretty quickly, which makes the whole technology really amenable to demand response. And provides additional economic value for the heat pump, because we can participate in demand response programs, help out the grid, and also make the whole system more cost effective, just because we're getting additional financial value through demand response.
We'll get to sort of payback and economics, but a question on sort of the carbon footprint side. We've got, again, roughly a 3x increase in efficiency. So and I'm just going to run numbers like easy in my head. If I said my boilers constitute 100% of my carbon footprint, just make the numbers easy, right? Just by shifting to the Skyven system, would I be able to literally cut my carbon footprint? And again, in this very simplistic thing, by 2/3?
If your boilers are, in some plants, boilers are 100% of the on-site, they call it Scope 1 CO2 emissions, the on-site CO2 emissions. And the Arcturus system, even when operated, utilizing demand response programs and turning it off, during peak grid demand, we're still able to offset 70-80%. Offset's not even the right word. We're basically able to shift the energy from natural gas to clean electricity for 70-80% of
right.
of a 24-hour day. So that's
so you got two factors working in concert here. One is efficiency reduces the overall, and the other one is the fuel shift from natural gas to whatever the grid is, and the grid is getting greener and greener and greener all the time. So if we assume the grid, and again, just numbers, if the grid is 50% renewable, you got 3x there plus another 50%. So rather than cutting it by 2/3, I'm literally cutting it by almost 80%.
That's right.
Okay.
Yeah, that's right. And then you can go even further. You can sign a combined solar and wind PPA, where you're able to procure clean electricity, and that kind of like boosts the overall decarbonization of the heat pump system even further.
Now, I don't mean to be disrespectful to anybody in the natural gas boiler market and things, but a natural gas boiler is pretty simple. It's not that hard from a technical perspective, not that complicated. You got a huge lift heat pump, lots of compressors and things like that. So I'm assuming that the capital cost for the same amount of steam is going to be different, even though the efficiency is better, between those boilers and the Skyven heat pump. For the areas we're looking at, and that's probably best in like areas like California and ERCOT and things like that, what does the payback period look like, Arun?
Yeah, so payback period depends heavily on the amount of, essentially depends heavily on energy prices, on availability of demand response, on ability to turn the system off when energy prices are spiking, as well as ability to leverage things like tax credits and incentives. So you have to kind of mix all of those factors together in order to determine like what is the payback and ROI on a system. So it can vary. It can be as low as a couple of years, and it can be as high as 10, 15, 20 years. And so it really takes digging into all of these factors in order to figure out, is this going to be economical at any particular site?
But let's take it from a different perspective. I'm a big corporation. Let's say I'm a food manufacturer. I use a lot of steam and everything else. I have set a goal. I'm going to be a zero carbon footprint, okay, by 2030, whatever the time is. And I want to do it really. I mean, what I mean by real is I don't want to just go buy RECs and offset it or plant trees. To me, that's a bit of greenwashing. I want to be zero carbon. Is there any way for me to do that with my process heat other than the Skyven system?
Yeah, I mean, you can, and a lot of manufacturers that are serious about decarbonizing have been looking at electric boilers.
Mm-hmm.
And electric boilers are not a new technology, and they utilize resistive heating in order to generate steam. So they have a COP of 1.
Mm-hmm.
And because electricity, tends to be on the average more expensive than natural gas, they can be hard to make economically viable. And so compared to an electric boiler, a Skyven system, has a COP of 2.5 to 3,
Right.
depending on the lift. And so you end up with a much more cost-effective system, even when the capital costs are taken into account.
Who is, the best target sort of customers? Who's, if I'm sitting here and I make ABC stuff, right?
Sure.
Who's like your perfect target customer?
Yeah, so we focus on 3 major industries. That's food and beverage production, pulp and paper, and chemicals.
Okay.
In those 3 industries, that they were all 3 are large industries. They tend to be steam intensive.
This is, of course, a new technology, revolutionary in a sense, I think, maybe a way to say. What didn't I ask you that I should have, because I'm not smart enough to ask the right questions?
Yeah, well, we get a lot of questions about, like, hey, is this, has this ever been built before? Has this ever been implemented before? Like no one wants to be the guinea pig, so to speak.
Mm-hmm.
And the technology is what I would call cutting edge, but not bleeding edge, in that it has been deployed at full industrial scale in a small handful of projects in Europe. And what Skyven is doing is taking those projects that show, hey, this tech, not only does it work, but it works with high reliability. We are building a standardized system that we are working to replicate across the 3 major industries: chemicals, food and beverage, pulp and paper, at sites across the United States.
Now, you had mentioned that early on in our conversation, margins in industry and process, especially those that use process heat, are pretty tight. Therefore, capital is always a big challenge to get in their capital budgets and things like that. I believe you've got a solution for those folks as well.
Yeah, that's right. So that's the energy as a service model that I mentioned at the start of the call, where we at Skyven will put these systems in at our own cost. So we cover the capital cost, and we cover all the operating costs. So that includes maintenance, as well as, and the big one is electricity cost. We at Skyven cover all of it, and then we bill our customers for the emissions-free steam that these systems produce. And we typically bill at rates that are less than the customer would otherwise pay for natural gas through their boilers. So it ends up being a profitable way to decarbonize steam.
Could I infer from that it's like kind of a no-cost decision for them?
Yeah, that's right. It would be a no-cost decision. I mean, at the end of the day, there's always a time and effort investment, right? There's no such thing as
there's disruption and there's projects and
and all that. But from a capital standpoint, it is no capital.
But you also said it's less expensive than the natural gas for the same equivalent amount of steam, right? So
that's right.
If I'm not putting up the capital and I'm not buying the gas now, and I'm paying for the steam, let's say it's on pound per steam, however you charge me, and that's less than the cost it was to generate that steam myself, I'm literally have an increased profit from going on this path of decarbonization. Is that accurate?
That's accurate. Yeah, that's what makes it profitable, right? It's OpEx savings without any CapEx.
Okay,
hard to find that kind of opportunity.
So let me summarize what I think I've got here is we have technology to help decarbonize process heat. It's roughly 2.5 to 3 times more efficient than the current standard way of doing it with boilers. With the utilization of renewable energy, solar, wind, and things like that, we literally could take somebody's process heat, steam-related process heat, from a significant carbon footprint to literally zero carbon footprint for no CapEx upfront and at an OpEx savings to them. Did I sort of paraphrase that correctly, Arun?
That's right. Yeah, sounds too good to be true. It is not too good to be true. It is a result of the physics.
Physics, right?
It's a result of the physics. Yep.
Okay. All right. Since it's not too good to be true, but people are always going to ask that question, and I'm not the one to answer it. How do they get in contact with you? Because there's going to be a lot of interest in doing this, as everybody has got decarbonization, corporate, goals and objectives and everything else. And I know, as you know, they're all struggling a lot with their process heat. So how do they reach you, Arun?
Yeah, thanks for asking that. So I'm not sure how to put my email address in this chat, but we're Skyven Technologies. That's SKYVEN. Our website is skyven.co. You can contact us via the website, or you can send an email to sales@skyven.co. Easy to remember.
And since this is a LinkedIn Live event, there is a Skyven LinkedIn page as well. So you can always visit that.
Yeah.
If anybody gets confused, you can always reach me at Exergy Energy, and we'll make the introductions and send you the contact information we need. Arun, thank you so much. Everybody, we really appreciate your time. And I hope this was beneficial. I mean, it's definitely one of the possibly only solutions to economically, profitably decarbonizing your process heat.